Hi, my name is Cheng. I'm the MI physicist of Imaging Research Facility at Indiana University. Today, I'm going to talk about a method of supervised denoising of DWS signal using deep learning. Okay, let me start the PowerPoint. So first, let's take a look at a practical problem. Now, MI images are acquired with multi-channel coils. We need to combine the signal from all the channels for optimal SNR. Normally, the sum of square method is optimal for if the SNR is not too low. However, this is not the case for diffusion MI when the B value is high. So people proposed other coil combine methods such as adaptive, combine, and sense1. Here we see that diffusion weighted image with B value of 2,500 is much noisier for using the sum of square coil combined mode than the sense1 coil combined mode. Actually, it's not just noisier, but also higher in signal magnitude. As a result, the ICVF map derived from the Nordi model has a lot of sealing artifacts here. Okay, the sealing effect mainly comes from the rectified noise. So what is rectified noise? We know that MI signal is complex. In the absence of signal, the mean and standard deviation of magnitude signal can be described by these two equations. Note that the mean value is not 0. This has an impact on the DWS signal. For instance, this figure shows that the decay of a DWS signal with B values. The signal should be 0 at very high B values, but because of the rectified noise, non-zero mean value, it fluctuates around a fixed positive value. So yeah, like this. So in the blue region, we can consider the noise to be Gaussian, but in the brown region, the noise is dominated by rectified noise. There are many denoising techniques for diffusion MI. I think Shreyas will give a review of that. The current denoising techniques can be roughly classified into two categories: unsupervised and self-supervised. The unsupervised denoising techniques include filtering-based methods such as BM4D, non-local mean method, the PCA-based methods such as MPPCA and LPCA. The self-supervised methods try to learn the noise structure from the data and remove them. So currently, this is the self-supervised method is relatively new. We have found that like the recently proposed SDN DTI and patch to self. However, none of these methods, to my knowledge, can effectively remove rectified noise. We have tried MPPCA denoising and patch to self denoising. They reduced the fluctuation of signal, but not the bias of rectified noise. Therefore, we still saw similar sealing effect in the ICVF map. Therefore, we propose to use a supervised deep learning method to correct for the rectified noise. To denoise a high noise DW dataset like this, we need a training dataset with no low noise, but with the same diffusion parameters. The deep learning method is based on a 1D convolution neural network. It applies on the fourth dimension of the DW dataset. So like for a DW dataset with n volumes, the DW signal of each voxel can be represented by a vector of n elements. And then the 1DCN applies on this vector, and each voxel provides one training sample. So even one brain DW dataset has enough samples for the training. The architecture of the neural network has two convolutional kernel layers plus two pooling layers, and then one flattened layer and one dense layer. So it's very, very simple. And we use mean square error between the output and the low noise signal as a cost function. The network was trained using TensorFlow. So to test this idea, we conducted two experiments. One is based on simulation, and the other is based on in vivo data. Okay, so here's the detail of the simulation. We first synthesized a noise-free DW dataset with 4 slices using the DW Poisson framework. The dataset consists of 4 B0s, B0 images, and 90 B1000 images, and 90 B2000 images. Then we added noise to generate 4 noisy datasets. 2 of them are with SNR 10 and 2 SNR 30. Then for each SNR level, we train the 1D CNN on one of the noisy datasets using a noise-free dataset as a ground truth, and then denoise the other dataset. As a comparison, we also denoise datasets using MPPCA. Here are the results of the denoised images and derived FA, mean diffusivity, and RCVF map for low SNR datasets and all other denoised for all the noise datasets and denoised datasets and the ground truth. So it shows that the denoising improves FA map on the low SNR dataset, but it has little effect on high SNR dataset. And the MPPCA fails to correct for rectified noise for low SNR dataset. And the 1DCN does a very good job in correcting this artifact. So the ceiling effect basically is gone. We can further compare the difference between denoised image and original image and the ground truth for MPPCA and 1DCN. Let's just focus on the CSF here. So we see that the MPPCA mainly reduces the signal fluctuation, but without knowing the ground truth, it is unable to remove the rectified noise. As see the difference between the denoised image and the ground truth. You see, basically this CSF rectified noise in the CSF is not corrected, but it's corrected by the supervised 1DCN method. Okay, for the in vivo data, we used the HCP lifespan protocol. So here it consists of 37 p-value of 1000 images, and the 37 images with B value of 2,500 and 6 B0 images. The resolution is 1.5 millimeter isotropic. And here we constructed the image using both sense1 and SSOs, sum of square. So we have, for each acquisition, we constructed 2 sets of images. And we also did 2 repetitions. We scanned 3 subjects, and we used 1 subject for training and applied the 1 DCN to the other 2 subjects for denoising. So here the SoS images is the noisy image, and the sense1 image was used as a ground truth for training. We applied both MPPCA and 1 DCN for denoising. And here are the results of 1 representative slice of the sum of square image, the sense1 image, and the denoised image for B value of 1,000 and 2,500. The denoised image is very similar to the sense1 image. And the average correlation coefficients between sense1 and denoised SoS image are much higher than the sense1 interscan correlations. Yeah, the sense1 interscan correlations is around 0.8, but the other one, the correlation between sense1 and denoised sum of square images is like about 0.95. The improvement can also be seen from the derived diffusion metrics, especially the ICVF. Here we showed FA, MD, ICVF, and OD. By looking at the images and the histograms, you can see that the denoised SoS image is very similar to sense1 image and quite different from the SoS image. So both simulation and in vivo data show that the 1 DCN denoising works well. In practice, the challenge is to find the low noise dataset for training, because simple averaging does not help on rectified noise. You do average, you still the rectified noise is still there. It's just added up. So as a demonstration, we did 2 experiments in which the high noise imaging protocol is typically adopted to save acquisition time, while the low noise images can be acquired with longer time. So experiment 1 is based on GRAPPA. The DWF protocol is based on the HTTP live stream protocol as well. So experiment 1, we acquired, the purpose of experiment 1 is to reduce the noise amplification from GRAPPA. So we acquired 2 runs, one with GRAPPA acceleration factor of 2, and the other run without GRAPPA. And therefore, the SNR of the images in the first run with iPad 2 is lower than the SNR in the second run with iPad equal to 1. And experiment 2 is based on multiband or simultaneously multi-slice acquisition. So we also have 2 runs. The MS option with an acceleration factor of 4 was used in run 1, resulting in 72 slices. And we did not apply SMS in run 2, but to have the same acquisition time, we have to reduce the number of slices. So the run 2, in principle, in theory, it has higher SNR than run 1 because it didn't use the multi-band acquisition. Okay, so here's the result of experiment 1. We only showed MD and ICVF because FA is not very sensitive to rectified noise. The denoised image showed a lot of details than the high noise image and even the low noise image. And the estimation of ICVF around here is largely corrected after denoising. The unestimation of mean diffusivity in this region is also corrected, but maybe a little overdone though. Okay, here's the result of experiment 2. The denoised image looks nicer. The ICVF map from denoised image is very similar to that of computed from low noise data. And so is the mean diffusivity map. You see the difference, right? Okay, so in conclusion, we propose a simple 1D CNN denoising method that works on the temporal domain. It requires only a small training sample size. Even one DWI dataset is sufficient. And it is very easy to implement. And it's very robust in correcting rectified noise if a good training dataset is provided. The code is available on GitHub. And if you have any question, just email me. I can answer it. I can provide any technical support with regard to this technique. And this work is collaborated with a lot of other people, especially Jen Wang, who was a postdoc here at RU about 2 years ago. Yeah. And yeah, thank you for your attention.